So this is an example that I got off of AP Classroom. I was like, okay, that's a good example. So fiddler crabs eat by sifting through sand to find food particles and then scooping them into their mouths. They do it really fast.
Reminds me of something.
That's not funny.
It's a little bit funny.
No, I'm not misfollowing you.
Wildlife biologists studied a random sample of one species of fiddler crab to estimate the speed at which they feed, measured in scoops per 30 seconds. For the 40 crabs in the sample, the mean was 67.65 scoops per 30 seconds. So they're doing like almost two a second. Yeah, they're sifting through this sand really quickly. And the standard deviation was 6.61 scoops per 30 seconds, creating a 90% confidence interval for the mean feeding rate of all fiddler crabs of this species. Does your interval support the conclusion that the average feeding rate for this species is more than 2 scoops per second? All right, so we need to make sure that we have all of the stuff. So, first of all, it tells you this is a random sample. Per the problem, I hate it when this decides that it doesn't want to write well. Per the problem, I have to write slow. This is a random sample of this species of fiddler crabs. I have to start typing it. It looks so bad. The sample size of 40 crabs is large enough for us to assume that the sampling distribution is nearly normal.
So why nearly normal and not normal?
We'll say normal. It's probably not perfectly normal, but that's fine. Is there anything else that we need to check?
Less than 10%.
Okay. 40 crabs is also less than 10% of all crabs of this type.
Did we ever get a free response question on the test that doesn't have one of these?
So what they do with ones like that is, and I've seen ones like that, they'll say, if inference is, if the assumptions and conditions are met for this, assuming the assumptions and conditions are met for this, do a confidence interval or do a test. And then in part B, they'll ask, was that really, did we really meet the qualifications? And that's almost always no.
Yeah.
But yeah, they're not going to ask you one where it doesn't, where they really want you to do the whole thing. That's a good question, though. Okay? So, the assumptions and conditions. Have been met for a one sample T interval for a mean. All right, and then we'll start listing the stuff that we know. We know that our mean is 67.65. You've got to be kidding me. Tried to write it 6 twice and it looked like that both times.
I'm curious, would they count off if instead of the X bar, you did like the Greek letter for mean, like the U? Would they count off?
Yes, because that applies to the population, not to the sample. So this was 67.65.
That was a really neat 6.
I had to, because when I tried to do it fast, it looked like I was a third grader on the back of a bumpy bus. And the standard deviation, S is 6.61. See? 6.61. What's the number of degrees of freedom?
39.
Yep. So between this and the fire drill,
I know.
degrees of freedom is going to be 39. And that's enough information for us to go ahead and just do the confidence interval. So I'm going to input the statistics. It's 67.65. The standard deviation is 6.61. Our sample size is 40. Oh, wait a minute. What was our sample size?
40.
It was 40? Okay. And I can't see it. Is it 95%?
90.
90? Okay. No, we're doing inference.
Why doesn't mine have the little test, right?
No, confidence interval.
Because it said we're looking for a 90% confidence. You go to one.
One mean?
Yeah.
Oh, I thought he did some,
And T interval.
So it gives us the t critical value, it gives us the standard error, gives us the margin of error, the degrees of freedom, all those different things. I would probably write down the standard error at the very least, and the t critical value, 1.68.
so we don't ever have to solve these by hand.
No. Now, I will say that occasionally what they'll write is they'll do a multiple choice question where they have all the different possibilities, and you've got to go, okay, which one of these is the right way to do it?
Like, it'll, okay.
Yeah, it'll substitute everything in.
Mm-hmm.
And then the standard error, what was the standard error? Did someone have that?
1.045.
1.045. And we get our confidence interval of 65 point, we'll call it 65.9 to 69.4.
Mm-hmm.
Yes.
So like if they made you find the confidence interval via like multiple choice and like they had it out like that, the right one would be like 40 plus or minus whatever the
40, no. 67.65.
oh
It's the mean
yes.
plus or minus, and then they would have the T star 1.68
Yeah.
times, and they would have something that would give you this standard error.
Yes.
What was the other number here?
69.4.
Okay, and then the question at the end, does your interval support the conclusion that the average feeding rate for this species is more than 2 scoops per second? Well, notice this is scoops per 30 seconds.
We're gonna divide it by 30?
No?
Oh.
Well, I suppose we could. So this is scoops per 30 seconds. I'm sorry, I was thinking doing the opposite way, but you could do that.
What's the opposite way?
You could figure out 2 scoops per second is how many scoops per 30 seconds. Right? So 2 scoops per second is equal to 60 scoops per 30 seconds.
That's easier.
Yeah, I think you can do it either way.
Oh.
So, does my confidence interval support the conclusion that the average feeding rate for the species is more than 2 scoops per second?
Yes.
Yes. Since our entire confidence interval is greater than 60 scoops per 30 seconds, it supports, and then I'm just going to write down exactly what they wrote down. It supports the conclusion that the average feeding rate for this species is more than 2 scoops per second.
Wait, so why again did you do 60 scoops per 30 seconds? I know you're finding 2, but like
So 2 scoops per second is 60 scoops per 30 seconds. And because my confidence interval is in scoops per 30 seconds, I want to be able to compare something that's also in scoops per 30 seconds.
so you're trying to find that it's more than 60?
Oh,
Yeah.
yes.
Okay, that makes sense. Yeah.
And the entire confidence interval is more than that.
Yeah, that makes sense.
All right. Let's do the last example.
Will we, oh, well.
Go ahead.
questions. Will we learn 2 mean proportions? Or,
Yes,
okay,
being able to compare proportions.
yeah.
Well, wait a minute. 2 mean proportions? No, there's no such
2
thing.
mean two means.
Yeah, we'll do stuff
Oh,
with
yeah,
two
not
means also.
proportions. Okay, that's what I meant. And then what's the Z interval stand for?
We've done Z intervals with proportions.
Yeah, why
So-
is it in here for?
In theory, all right, so let's real quick go back to that. So what if we had done this as a Z interval? Let's see if we get anything different. So we're still inputting statistics. It was
67,
67.65.
6.61.
6.61,
And then 40.
and a confidence level of 0.9.
Big
Uh-oh.
points.
Oops, I hit 0.0. And it gives us a Z critical value. Notice that the Z critical value there is really pretty close to the T, and the standard error is also really, really close. Let's see what sort of confidence interval they have. 65.9 to 69.4.
So that's basically the same.
And why is that?
That means this sample can go for the whole population?
Nope.
Oh.
I don't know.
What happens as our sample size becomes larger to a T distribution?
Becomes more normal.
Becomes more normal. This is big enough to where the difference between a T and a Z is basically negligible.
Wow.
If you actually turn your notes back to the previous page, what is the degrees of freedom that is closest to the normal one that I put up there?
20. So the biggest.
20. This has 39 degrees of freedom. It's going to be so close to normal that you could use a normal for it.
Wow.
Oh, so Z-score is for perfectly normal.
Z-score is if we know it's normal. And if you have a large enough, sample for your means, you could use it.
But if it, okay,
It's better just to go ahead and always use the T for the means
just in case.
and always use Z for proportions. Then you don't have to think about, wait a minute, which one should I use?
Okay.
Okay, but I'm glad you asked the question because it's like, okay, yeah, this is such a big sample that it's basically going to be the same. All right. An article on the internet claims that the average vertical jumps, I guess that should be singular, for teens is 15 inches.
Really?
Yeah, I don't believe it. I think when I was a teenager, I don't know, my vertical might have been, 4 inches. Never was much of a jumper. All right, so a group of statistics students at a large high school selects a random sample of 20 students from their school and measured their vertical jumps. The students in the sample jumped an average of 15.8 inches with a standard deviation of 2.33 inches. Do these data provide convincing statistical evidence? Anytime you see that, you're thinking, I need to be doing a test. That the average vertical jump at this high school differs from 15 inches. All kinds of important words in there. And they've given you a data table.
You can use that.
Yeah, you're going to have to use the data table.
Okay, we got to put it into the thing. We have a data set. We have something perfectly for that, correct?
Yes, but we don't have to put it in to start with. We can do it in on there. You can do it as part of going through
Right.
the test. You don't have to.
Right there, right? Use data set.
Indeed. All right, but before we start doing that, what do we have to do?
Make our hypothesis. Oh, and check conditions.
Check the conditions, and we need to set our hypothesis also. All right, so shall we start with the conditions?
Yes.
All right, Problem states this is a random sample. Of students from the school. And I can say the school because it's the only one they're talking about. Okay? What else?
Less than 10%.
All right, so 20 students should be, again, you always kind of hedge your bets, less than 10% of the student body for a large school.
And 20 students is large enough?
No, it's not.
Oh, just kidding.
Remember, 30 is sort of our desired, we'd like to have at least 30. So what are we going to do instead?
Oh, we're gonna do the normal model thing with the histogram.
We're going to do what? I'm sorry?
The normal model thing with the histogram.
So we'll look at a histogram to see if this is nearly normal or not. So we are going to go ahead and put that stuff in and look. The nice thing is if you put it into your statistics, I believe it will come over.
Right. Oh yeah, I did yesterday.
Yes.
These kids can jump. Goodness.
I'm sorry.
I said these kids can jump. They got like 18 and 19 and
Yeah.
22.
Like, is this some sort of basketball academy or something? I'm going to look at the statistics on this to make sure that I've got what they have. So they had a standard deviation of 2.33 and a mean of 15.8. Let's see if I've actually got that. Mean 15.8. Standard deviation of 2.33, yep. And it's the sample standard deviation, right? Not the other one. All that other kind of stuff. So I'm going to look at a graph. So let's look at a histogram, but let's also look at a normal probability plot.
Histogram's not looking good, Mr. Davis.
It's not a great histogram.
It's got an outlier.
Well, now wait a minute. We don't know that's an outlier, do we?
No.
Oh wait, no, we don't. We have to do the
2 standard deviations.
yeah.
So let's go back and change the graph to a box plot. That'll tell us if it's an outlier or not. Nope, not an outlier.
Mr. Davis. Oh, never mind.
And let's go back and look at a normal probability plot.
That's pretty close.
The normal probability plot's pretty straight.
Yeah, it's fairly.
No.
Okay, residuals one is the one that you don't want it to have a straight line,
Right.
because it's the expected minus, right? Or no?
We want a plot of the residuals to be just totally random. So what this does is it does an expected z-score and your actual z-score. We want those to be fairly close together so that when we take one over the other, they're pretty close. All right, so I would just say this: if you don't want, especially if you don't want to have to draw the histogram and argue that that's fairly normal, it's normal-ish, and there's a lot of ish in that one, but the normal probability plot is pretty straight. So as the normal probability plot is reasonably straight, we conclude that our sample has a fairly normal distribution.
So I'm curious, what if the histogram was just like uniform?
If it was totally uniform,
Yeah.
then your probability plot wouldn't be straight.
So then that's a bad thing.
Yeah.
Okay.
So you'd go, no, we can't do this. So the assumptions and conditions are met. For a one sample t-test for means. All right, so what is our null hypothesis?
That the mean is equal to 15?
Yeah, our null hypothesis is that the mean is 15, and you can use mu for that, and probably should. Don't use x bar for that, because x bar is for your sample. And we know that the sample is not 15. What is our alternative?
It's not equal to 15.
Yeah, that mu is not 15. Basically what they're saying is this far enough away from the mean to convince us with a sample this size that there really is a difference at this high school as opposed to some other, as opposed to all high schools, okay? Where mu is the mean vertical jump of students at this high school. All right, we'll have to leave it there, but you know how to finish it from there. It's all, put it in the calculator from there.
So would it end up being different?
On this one, it turns out that our p-value is practically 0. So since our p-value is practically 0, then whatever it doesn't really, whatever alpha level we chose, which we didn't do yet, but it's going to be less than that, so we're going to reject the null and find that there is a difference.
I'm Stokes. Have a good day.
Thank you, you as well.
Okay.
Okay?